Hi everyone, in this video I'm going to motivate why we can't form the Hessian explicitly for large-scale optimization or for large-scale inverse problems. And this motivates why we talked about Newton CG, because remember that in iterative solver you do not need to explicitly form the matrix. All you need is its action on a vector. So that'll be the approach. We won't form the Hessian explicitly. We will compute its action on a vector. So let's look at this inverse problem where our model parameter is m. And let's just go ahead and go straight to the discrete case. So we discretize a vector u in Rn. We have possibly a reduced dimension representation of m, of our model parameter m, which is this source function here. And we have our data d, which again possibly lie in a different sample space. General d is going to be much less than n. And so the forward problem can be rewritten as au equals dm, and this d here is basically how you map m into the higher dimension. So this is d is in the case where m equals n and you're using finite difference methods. D is just the identity, right? You just observe m, but you might interpolate. You know, if m is less than n, you might interpolate m to fit within u. That's all d is doing. And then a is discretizing this differential operator some way. So u is equal to a inverse d. Now in our context, A is a square matrix. D maps m vectors to n vectors. And then recall that our job in inverse problems m is to solve this minimization problem. And we'll go again straight to the discrete case here. M transpose R M, where since we haven't touched this in a while, this is the observation operator. So an example here is for subsurface imaging. You solve, this is depth z, x, and y. I'm not even sure if that's a right-hand coordinate system, but you get the idea. And the point is you have receivers here on the surface, right? Because if you want to figure out what's underneath the subsurface, like an aquifer or a salt body or these types of things, you want receivers at the surface. Otherwise, you just drill straight in and see if you found it, right? So, so the idea here is now in the continuous case, BU is going to be u of x, y, 0, and of time. So this is z equals 0. And that's all it is. So it can be observations in the boundary. It's just where you're observing. In the case where you're observing everywhere, B is just the identity. So B here, so notice that, so D is in RD. So we map n vectors to D vectors. So output is D, input is n, and R is in R m by, sorry. It outputs the data dimension. Okay, so I'm going to go ahead and drop these tildes now because we're we're discrete for the rest of this video. So let's just write this as 5m is 1/2 bu minus d transpose one other thing. A equals A inverse D. U equals A inverse D. M, so we can eliminate this dependence. And I'm going to set C equals BA inverse D plus alpha over 2 MR transpose M. So the normal equations, we're minimizing M in R M of phi of M, and so this gives us the normal equations. If you're not familiar with them, just look up that term, normal equations. All you're doing is you're taking the derivative with respect to each component of M and setting it to 0, right? It's Calc 3 stuff. So normal equations give you this solution. The minimizer satisfies this matrix equation. Equals C transpose D. Okay, so what does this look like? So we're just going to look at the dimensions here. So C transpose C can be D transpose A inverse transpose B transpose B A inverse D. Now, in this case, we typically are going to have I've overloaded notation. So this is tilde, right? That's the matrix. D is the actual dimension that I'm ascribing to the data. So typically we have sparse observations, which means D is much less than or equal to M, and we ideally want to parameterize our model parameter in as little dimensions as possible. So this last inequality isn't necessarily true where you have M less than or equal to D, but typically D is much less than M. So we have a system that looks like the following. We have, so the action of this vector has skinny D, A inverse is square, which that's not drawn as square, but it should be. And then, oh gosh, move this all the way over to the right. So we have skinny D, or tall D, square A inverse that's large, wide B, tall B transpose, A inverse transpose, n by n square, and then D transpose should be wide. So the point is, the reason why I draw this out, and if that gets a bit confusing, just think about where your input and output space are, because it's it's six steps. But the whole point here is that we have these dominate the cost of the Hessian. So here C is the Hessian. I'll call this C is the Hessian of data misfit, and R is the Hessian of regularization. So one thing I forgot to mention is that R is in C is in R. D by M, and so C transpose C is in R M by M. Means R is in M by M. So the reason why this is the Hessian is because if you just look at this equation, you get an M transpose M, which makes that look like a quadratic. So if you take two derivatives, you get C transpose C, which is that higher order term. It ends up being the Hessian of the data misfits in the discrete case. So let's see what the cost So basically, I just want to motivate in this video why we can't store the Hessian. Is why we want to use iterative methods here. So let's consider when, for simplicity, that we want to solve a 3D inverse problem. So we have a 100 by 100 by 100 grid, which honestly is quite small in general. And let's assume that forward solve costs it takes 1 second to create a forward solve. Now, to form the Hessian, what we then have to do, right? So to form C transpose C. Well, actually, so to form C in D by M, you need to compute C acting on E1 or EI for I from 1 to the min of D and M. Why the minimum? Because then you can basically so you need the let's say that M was greater than D, you can compute C transpose and then just directly get it. But the point is, if I give you a matrix C, that is a representation for C. So here in this case, we have M equals D. Equals 10 to the 6th here. Why? Because 100 times 100 times 100 is 10 to the 6th. And so we need 10 to the 6th in order to compute the Hessian here. You need this A inverse, and if we want to actually compute the full Hessian here, C transpose C, we have both of these. So in this process of computing for each basis vector, we have to compute 2 PDE solves. But in computing C, we only need to do 1. So that's 10 to the 6th forward solves. We don't need to do the adjoint part explicitly, because then we could just multiply the two matrices. And that's 12 days since each forward solve cost 1 second. So that's a long time. But it's not totally unreasonable. A 100 by 100 by 100 grid is something you can solve on a laptop. So really, that's not a very large system. If we just scale this up to 10 to the 8th, that becomes 1200 days, which is 3+ years. And that's assuming that we have a pretty fast forward solve. So we really can't we can't go through this process of forming C. We also can't store, so we can't construct the Hessian C. And even if we could construct C, we couldn't store it, because we need 10 to the 6th by 10 to the 6th entries. In general, C transpose C is dense, and C is dense. So if we do double precision, 8 bytes per entry, that's 10 to the 13th bytes, or 10 terabytes, which again is only for a 100 by 100 system. If we crank this up to something quite interesting, like a global seismic inverse problem or something, let's say it's 10 to the 8th. 8 bytes per entry, so that we multiply. So that's 10 to the 16th. 8 bytes is roughly 10, so that's 10 to the 17th bytes. That's 100 petabytes. That's way too much. That's more than most supercomputers. That's way too large. So we can't store C either. And finally, even if we could store C, we can't factor it. We can't compute its LU factorization. Because we need to solve systems. We need to solve the system C transpose C plus alpha R equals C transpose D. So we need an LU factor. This is if we wanted to do direct solver. So this is 10 to the 6th cubed is 10 to the 18th. Now, if you have an exaflop, that's 1 second to compute that. But that's all of Frontier, which is the fastest supercomputer in the world as of when I made this video. That's all of Frontier, and that's for a 100 by 100 by 100 grid here. So, which again is quite small. So let's look at the case where we crank this up by 100 times. We cube that. This is 10 to the 24th. So we need 1,000,000 seconds equals 12 days with all of so that's all of Frontier at peak. With all of Frontier at peak, which you're not going to get peak, right? That's assuming you take this multi-million-dollar supercomputer and it's at peak the whole time. It's still going to take 12 days to factor it, and that's after we waited 3 years to actually construct it. So the point is, an iterative solver we only need the action of C transpose C on a vector. Okay, so this is why we wanted Newton-Krylov. And in order to compute the action, we solve, right? So think about what this C transpose. So C transpose C is D transpose, A inverse transpose, B transpose B, A inverse So let's assume that, right, D, B transpose B, and D transpose are cheap in our context compared to the PDE solve. So in order to get the action of A inverse D on a vector P, or let's call it Z, then we solve the system A inverse dz equals x. Yeah, we solve a system of the form ax equals dz. And then to compute A inverse transpose B A inverse D, we take that x, we perform B transpose B on that x, because that x is A inverse dz, and then we compute A transpose y on that value. And then at the very end, we compute D transpose of that. So ultimately, that is one forward solve and one adjoint solve. So that's two PDEs of roughly the same complexity for most cases. So that's 2 seconds. Now, of course, we're solving this iteratively, so we have to, it's ultimately going to be 2 seconds times the number of iterations we need, but ultimately, in practice, you're not actually going to have a million iterations. So that, hopefully this motivates you of why I pushed Newton-Krylov for large-scale inverse problems in the previous videos, because of this cost. Now, of course, in some applications, the Hessian might be this. You might not get convergence in this case, which is why some people would promote gradient descent in this case, because you don't. Or a quasi-Newton method like LBFGS, so that you can avoid all of this, because the Hessian is pretty expensive to compute. So thank you guys for watching, and hope to see you in the next video.